The last thing we discuss in Unit 2 is the first part of Chapter 3, Section 6. Chapter 3, Section 6 covers inequalities, both polynomial and rational inequalities. But we're not going to talk about rational functions and rational inequalities until we get to the next unit. So we're just going to divide off and talk about polynomial inequalities right now. Consider the graph of this polynomial function and think about what you know. Well, this graph should have arrows on the end, first of all, because it's polynomial. So we know that the domain is going to be all real numbers. And I can see, because it keeps going, that this function also has a range of all real numbers. I can tell some things about the degree. Because it has two terms, I know that the degree has to be at least 3. And I know it has to be an odd degree because one end is down and one end is up. So it would have to be degree 3, degree 5, degree 7. I know that my leading term is going to have a positive coefficient, because overall it's an increasing function. I start low, I finish high. I know some things about the roots and multiplicity of those roots. I know that I have a root at -6. I have a root at, it looks like, -3. And I have a root at positive 1, 2, 3 as well. And since they just cross at each of those roots, they don't slow down, it looks like they each probably have a multiplicity 1. So again, probably third degree. I know that my y-intercept is right here. It looks like my y-intercept is at 0, maybe -13.5-ish. It's close to that. So these are all things that I know just by looking at this graph. Now we're going to talk about the graph in terms of inequality statements. For what intervals, and remember when I asked that question, I'm going to give intervals on the x-axis, and I'm talking about what y is doing. So for what intervals is my y value greater than or equal to 0? Well, greater than or equal to 0 means at or above the x-axis. So my y values are at 0 here, and they're greater than 0 anything that graphs above that x-axis. So this piece of my graph and this piece of my graph is going to be greater than or equal to 0. So for the interval on the x-axis from -6 to -3, or +3 to +infinity, the graph is above the x-axis. Now I included those endpoints because my inequality symbol is or equal to. What if my inequality symbol is just greater than? Well, it's the same intervals, it's just that I don't include the endpoints, because at those locations the graph is equal to 0. The function value is equal to 0. What about this next question? For what intervals is my function value, my y value, less than or equal to 0? Well, the function value is less than or equal to 0 anywhere the graph is below the x-axis. So here my graph is less than or equal to 0. When I give the interval, I'm giving the interval on the x-axis at which that happens. So my intervals are -infinity up to -6 inclusive, because it's or equal to, or -3 to +3, both of those inclusive, because that's where my function values are equal to 0. And then what if I take away that or equal to? Well, I've got the same intervals, just not inclusive. So I use parentheses instead of square brackets. Let's evaluate these two functions, and then we're going to look at the back and we're going to talk about our test point method. Solve f of x greater than or equal to 0. Where is my function greater than or equal to 0? Well, this piece above the x-axis, this piece above the x-axis, and look at that, it's equal to 0 right there. So I have 3 places. My function is greater than or equal to 0 for all x values from negative infinity up to, and that looks like negative 3, and because it's or equal to, it's inclusive. Or that single value at 2. So if I have a single value, I put it in fancy braces. Or from 5 inclusive to positive infinity. What about if I changed that question a little bit and made it for where is f of x just greater than 0? Well, it's going to change those square brackets to parentheses, and if it can't be equal 0, I don't include 2. So that would just be negative infinity to negative 3, or 5 to positive infinity without including those places where it's equal to 0. Now let's look at g of x. Solve g of x less than or equal to 0. Well, less than or equal to 0 is where the graph falls at or below, and that falls below right there. So I've got the x coordinates, the x interval from negative infinity up to and including, because it's or equal to, negative 5, or from 2 to 3. Now if I change that to just less than, I'm not going to lose any values. It would just change my square brackets to curved parentheses. Let's talk about the test point method. What if I'm not given a graph? Well, if I'm not given a graph, I can use the test point method. Now here is my disclaimer. Test point method for solving polynomial inequalities is kind of redundant. We can do it by creating a graph, because at this point we should be pretty comfortable with creating those graphs. However, when I get to rational inequalities, I want the test point method because it's way more work to create the graph for a rational function than it is for a polynomial function. I need to practice the test point method now so that I understand it when I get to rational inequalities. So I'm going to make you practice it now. I want you to show me test points so that when you get to rational inequalities, it will be simple. Test point method is not that hard. You're going to express the inequality as set to 0. So if it started with a constant over here other than 0, you're going to move everything over so that it's set to 0. Then you locate the boundary points by setting each factor equal to 0 and solve. Boundary points are equal to my zeros or roots of the function. I'm going to put those boundary points on a number line. I don't do my xy coordinate plane, I just do basically the x-axis as a number line. Then I'm going to test a point within each interval to see if the graph, the function value, would fall above or below that number line. So would it be positive or negative in that interval? The solution set will include the intervals that satisfy the inequality. Let's do this first example. The first thing we need to do is set it to 0. So I need to move my 20 over so that I have x squared minus x minus 20, and I'm interested in where that is greater than 0. So I'm interested in positive values, function values. I need to factor this to find out what boundary points to graph on my number line. My factors come out to be x minus 5 and x plus 4. So my boundary point values are going to be negative 4 and positive 5. And I put those in order from least to greatest on my number line. So I need a number line here. And I need to make sure I do least to greatest. So I'm going to use negative 4 and I'm going to use positive 5. Notice that when I put 2 boundary points on my number line, I divided my number line into 1, 2, 3 intervals. I need to check a test point in each interval. Okay, so let's pick test points to check. I just need a point in this interval, a point in this interval, and a point in that interval. I'm going to pick easy values. 0 is easy to plug in and check, so I figure out where 0 would be, and I'm going to check it. Then I need something big out here that's going to be obvious. So a lot of the time I'll pick like negative 100 and positive 100 because those are so far out there that it makes it simple for me to figure out whether values in that interval are going to be positive or they're going to be negative. Now to test the points, I plug these given test values into my factors to see if what comes out is positive or if what comes out is negative. For this first interval, if I plug in a negative 100, this would be a negative 100 minus 5. Well, that's obviously negative, and it's negative 105, but I don't care. I just care that it's negative. And then I have negative 100 plus 4. That is also negative. If I multiply together two negative values, I get out a positive value, which means every number in this interval, every function value is going to be positive. The graph for this interval will be above the x-axis. Now let's move to our second interval, which we chose 0 as our test point because it falls. It falls in this interval and it's easy to check. 0 minus 5 is negative 5. 0 plus 4 is 4. And a negative times a positive is a negative. Specifically, it's negative 20. But we don't care. We just care negative. Now we check this third interval, and we're going to use a positive 100 to test. 100 minus 5 is 95, but what's important is that it's positive. 100 plus 4 is also positive. It's positive 104. We don't care what 95 times 104 is. What we care is that positive times positive is going to give me positive values in this interval. Now I go back and I say, okay, what am I interested in? Well, I'm interested in where the values are, whoops, not that one, right here, where the values are positive, greater than 0. Well, they're greater than 0 here and here at the ends, not in the middle. So the intervals that satisfy my inequality are from negative infinity up to negative 4, and I don't include negative 4 because it's not or equal to, or 5 to positive infinity. Now, because this is a polynomial inequality, we could stop and we could say, oh, look, it's quadratic. It's a parabola opening upward. So if I were to sketch my graph is going to look like that. And it mimics those positive, negative, positive values we found. I want you to practice the test points. Don't rely on structuring the graph, because I want you to practice doing those test points before you get to the rational functions. Let's do the next example. Solve the inequality, and it's already set to 0 for me, so that's lovely. I just need to factor it to get my boundary points. Well, factoring a third degree polynomial, that's a little bit more work. I have a couple of options for this one. Now, I can use my synthetic division, my P over Q for my values, but notice that I have 4 terms. Anytime I have 4 terms, I want to try to factor by grouping. Factor by grouping, I pull out the common factor here, that's going to be x squared, and it leaves me with x plus 7. And I want to have a common factor that matches here. Well, if I pull out a negative 1, I have x plus 7 again. And then my next step for factor by grouping is to pull together what I pulled out. So x squared minus 1, and then that common factor is x plus 7. X squared minus 1 is difference of squares. It gives me x plus 1 times x minus 1, and then I have x plus 7. I'm interested in where that is less than 0. What are my boundary points? Well, this would be negative 1, positive 1, negative 7. From least to greatest, I would say negative 7, negative 1, and positive 1. 3 boundary points results in 1, 2, 3, 4 intervals to test. So I need to go through and I need to pick values in each of those 4 intervals to check. 0 is always easy. It falls here. I'm going to do my large values at the ends. And now I need a number between negative 7 and negative 1. It truly does not matter what you pick. I'm going to pick negative 3. Let's test these intervals. I have 3 factors to plug in to test. So if I plug in a negative 100, that's a negative, that's a negative, and that's a negative. 100 plus 1 is negative, 100 minus 1 is negative, excuse me, negative 100 minus 1, negative 100 plus 1, negative 100 plus 7. All those give me negative sums. And when I multiply a negative times a negative times a negative, I get a negative. So that interval is negative. This one I have to pay a little closer attention to because I need to make sure that I end up with the correct value. Negative 3 plus 1 is negative 2. Negative 3 minus 1 is negative 4. And negative 3 plus 7 is positive 4. So I have a negative times a negative, which is a positive times a positive. So this interval has all positive values. Now I do 0. 0 plus 1 is 1, 0 minus 1 is negative 1, 0 plus 7 is 7. Positive times a negative times a positive gives me all negative values in this interval. And finally, I plug in 100 just because it's big. That's going to be positive, that's going to be positive, that's going to be positive. Because 101, 100 minus 1 is 99, and 107. If I were to multiply all that together, that's going to give me a positive value, which means every value in that interval is positive. Then I check to see what I'm interested in. Well, I'm interested in values less than 0, so I'm looking at those negative intervals. That's where my graph would fall below the boundary line, below my x-axis. So I have from negative infinity up to negative 7, or not inclusive because it's not or equal to, negative 1 to positive 1. And those are the intervals where my y value is negative, the graph would fall below the x-axis. It satisfies my inequality. Now I'm not going to talk you through the third one. I'm going to show you the boundary line and I'm going to give you the results. It's already factored for you, so you don't have to do that work. You go least to greatest, remember. You're going to pick a test point in each of those 4 intervals. And this one's a little tricky because you're going to have to pick negative 3.5 would be the best, easiest thing to do there. 0 could go here, anything between negative 8 and negative 4, and anything down here less than negative 8. When you get done, when you have solved this, and I want you to work through it on your own, your result should be negative infinity to negative 8 inclusive, or negative 4 to negative 3 inclusive. Why are these inclusive? Well, because for this inequality we have or equal to.